The next thing that we want to look at is vectors in 3 dimensions, not just 2 dimensions. Okay, now we want to look at how we write or how we draw a coordinate system in 3 dimensions. And you can see that I've got a normal vertical and horizontal axes here, and then I've got a third axis coming downward at a diagonal angle, roughly 45 degrees-ish. And that downward diagonal is representing the axis that's coming perpendicularly out of the page. Of course, we can't physically draw an axis coming out of the page, so we draw it with perspective, and so hopefully that vector into a sum, tail to tip twice, of a vector that is in the xy plane here. So here is the xy plane, and I have a vector that is in that plane that's directly underneath my a vector. It's like if there were a spotlight up above shining downward, this would be a shadow on the xy plane. And so I have my vector A that has its shadow, and the technical mathematical term for that shadow is the projection. We say that this vector A sub xy is the projection of A onto the xy plane. And then we have this other vector, AZ, which is parallel to the z-axis and therefore perpendicular to this AXY vector. And so A sub xy plus A sub z equals A, according to tail to tip twice. And that gives us this vector A broken down into a simpler vector sum. Okay, here we're considering just the projection A sub xy, the vector that is in the xy plane. And if I have my 3 coordinate axes, I can note that my x-axis is pointing out of the page, and it will have a unit vector x hat. Y hat will point along the y-axis, z hat will point along the z-axis. Now, if I consider my AXY here, I can note that that vector, A sub xy, can be broken into 2 mutually perpendicular vectors, A sub x, which is along the x-axis, and A sub y, which is along the y-axis. And so I can say that this vector A sub xy is equal to some A sub x in the x-hat direction plus A sub y in the y-hat direction. That's just tail to tip twice. The A sub x vector plus the A sub y vector is equal to the A sub x vector. And remember, this is the projection of our original vector, which was up in the 3-dimensional space. Now, if this A sub xy is this vector here, we know that this is going to be a right angle because the x-axis and the y-axis are perpendicular. And so by the Pythagorean theorem, this projection, A sub xy, is equal to ax squared plus ay squared. Okay, now we can consider the vector A, which is broken up into our A sub xy and A sub z. And of course, A sub xy and A sub z are going to be mutually perpendicular. And so this makes another right triangle. And so we can say that the vector A is the vector A sub xy plus the vector AZ, and that A squared is equal to A sub xy squared plus A sub z squared. Now what's interesting about this is that we just saw in the previous slide that A sub xy squared is equal to ax squared plus ay squared. That would be the x component and the y component of the vector. A sub z obviously would be the z component of the vector. But our end result is that a squared, this hypotenuse, is axy squared plus az squared, but axy squared has an x component and a y component, and we can just plug in that a sub xy squared is ax squared plus ay squared, and that gives us this result. The vector A squared is equal to ax squared plus ay squared plus az squared. That is the three-dimensional Pythagorean theorem. And it works just like the regular Pythagorean theorem. Okay, let's look at an example. We have a vector whose components are given by the vector A is 6x hat plus 9y hat plus 9z hat. And we want to find what's its magnitude, what angle theta does it make with the z-axis. So my vector A is in three-dimensional space, and there's going to be, it's going to make a plane with the z-axis, and in that plane there will be this angle theta. And so the angle theta is from the z-axis to my vector A. Now, if I consider this projection of A into the xy plane, which we are calling A sub xy, that projection makes an angle phi with the x-axis. And so the problem is find the magnitude of A, find the angle theta that it makes with the z-axis, and then find the angle that its projection makes with the x-axis down in the xy plane. So to do this, we're going to use that three-dimensional Pythagorean theorem. So we saw previously that a squared is equal to ax squared plus ay squared plus az squared. So in order to get the magnitude of A, we're simply going to want to take the square root of both sides. And so the square root of there and the square root of there. And the square root of A squared is just the length of A. And so that's what we're looking for. So by the three-dimensional Pythagorean theorem, we can say that A magnitude is equal to 6 squared plus 9 squared plus 9 squared. That's AX. Here we see AX, AY, AY, and AZ. So you simply square all the components, take the square root, and that gives you the length of a three-dimensional vector. And then plugging in the numbers, we get 14.1 units, and that gives us the magnitude or the length of this vector A. Now in this picture, I've taken my vector A sub xy and I have put it up above. So I've simply shifted it parallel, and this is essentially, I've drawn like the parallelogram method. So here's my AXY, here it's repeated, here's my AZ, here's my AZ repeated. So I've got the parallelogram method here. But if I look at this piece and that piece, I can see that it makes a right triangle. There'd be a right angle there, and that gives me my angle theta. So this is the opposite side to the theta, and this AZ is the adjacent side. And so we want to find the angle theta. That's just going to be given by the cosine of theta, which is equal to the adjacent side over the hypotenuse side. And there should be little absolute value bars there, so let me draw those in. And so we've got the length of AZ divided by the length of A gives me the cosine of theta. And so I simply can plug in the numbers. We saw in the last slide that the magnitude of A was 14.1. The AZ component is 9. So plugging in the numbers, we get that theta is equal to 50.3 degrees. Then similarly, looking at the projection in the xy plane, we know that it's made up of the subtriangle a sub x plus a sub y, and we can simply say that we know the components, we know the x component and the y component, and so phi is, that would be the adjacent side is a sub x, a sub y would be the opposite side, and so simply plugging in those values into the tangent of phi, we can solve for phi. Phi is going to be the arctangent of 9 divided by 6, and that gives us 56.3 degrees, and that basically is the solution to the question. Now let's look at another example of using a three-dimensional vector. Here's an example. Determine the components of a unit vector that points in the same direction as the vector 8x hat plus 4y hat minus 2z hat. Now that's actually, it seems like a hard problem. I want to have this vector, and it could be any vector in space, but in this particular vector it is this vector here, this v, and we want to find the unit vector that points in the same direction. In other words, there must be some v hat whose length is 1 that points in the same direction as this guy. What would be the components of v hat? That's the question. So, in general, we know that we can express a vector, any vector, as its magnitude and its direction v hat. So we've got v magnitude and v hat. So I want to find v hat. I want to find this guy. So I simply divide both sides by v magnitude, which, remember, v magnitude is the magnitude of this guy. It's just a scalar. And so I can divide both sides by that scalar, and if I do that, I will have solved for v hat. Now, what is v magnitude? It's simply the sum of all the components squared, and then take the square root. And this is 8 squared, 4 squared, 2 squared. Technically, this should be minus 2 squared, but what happens when you square a minus 2? You get 4. What happens when you square 2? You get 4. So when you're doing this, you can really ignore those minus signs because they're going to go away anyway. But your final result for the magnitude is simply 9.17. Now, how do I find the components of the unit vector? I simply take my vector v here and divide each of its components by 9.17, and that'll give me my answer. So let's do that. I've got my vector v, which is right here. It's 8x hat plus 4y hat minus 2z hat. My v hat is going to be that vector v divided by the magnitude of v, and so I've just written my vector. I divide each term by 9.17, and this gives me my result, which is v hat equals to this, 0.87x hat plus 0.44y hat minus 0.22z hat. Now, let me ask a question here for you guys. What would be a way to test to make sure that this guy really is a unit vector? How do I know that this, if I screwed up some algebra, if I plugged a number into my calculator wrong, is there a way I could check that other than just redoing it? Well, we can actually. What would be the magnitude of v hat? It would be equal to 1. So the magnitude of v hat would be equal to 1. So all I have to do is square that, square that, square that, take the square root, and that should be equal to 1. If we have done this correctly, that will be a unit vector. Its length will be 1. And so I would recommend that you guys do that test, show yourselves that this is indeed a unit vector, and also get a little bit of practice in using this three-dimensional Pythagorean theorem.